Hi, I'm doing a short video presentation on IPv4 addressing. I'm going to be covering IPv4 addressing basics, how the IPv4 addressing rule works, the difference between public and private IPv4 addresses, and a small introduction to IPv4 subnetting. In this slide, we cover the basics of IPv4 addressing. So what is IPv4 address? It is a numerical label assigned to a host identified as a node on layer 3 participating in a network using the IP protocol defined in RFC 760. An IPv4 address is composed of two parts, the first being the network ID followed by the host ID. The network or subnet mask defines the bits which belong to the network ID. It consists of 32 bits or 4 octets. An octet is 8 bits in length. The network ID or the host portion cannot be all zeros or all ones. Examples of IPv4 addresses include the following. The private IP address of 192.168.1.1 with a mask of 24. The public IP addresses of 74.125.226.64 with a mask of 8, and 173.194.75.94, the mask of 16. So with the private IP address of 192.168.1.1 with a mask of 24, we see that it could be represented in two forms, in decimal form and in binary form. So taking the first octet in binary form, we can derive 192. So the 8th bit of the first octet has a value of 128, and the 7th bit has a value of 64, so 128 times 1 plus 64 times 1 equals 192. And that's how we get the first octet in decimal form. So let's go on to the second octet. The 8th bit has a value of 128, so 1 times 128 is 128. 0 times 64 is 0. 1 times 32 is 32. 16 times 0 is 0. And 8 times 1 is 8. So 8 plus 32 plus 128 gives us 168. And that's how we derive this, the second octet in decimal form. And the third and the fourth octet have each a value of 1. And that's how we get 192.168.1.1. Okay, so let's go on to the next slide. Here we have a chart on IPv4, and it divides it up into the 5 different classes of IP addresses, and a class represents an IP address range. So we can start off with Class A, and actually before we do that, the Class A, B, and C are unique in the sense that these are the classes which are used to or assigned to hosts. Class D is used for multicast IP addressing. Class E is used for experimental purposes. And the classes are defined using a binary rule, and they have a first octet range based on that binary rule. And using the default subnet mask, you can derive the number of networks, the number of hosts per network, and the total network and host combination. So let's begin with Class A. So for Class A, the rule says the first octet, in the first octet, the 8th bit has to have a value of 0, and you get the first octet range from 1 to 126. And the reason why it doesn't start from 0 is we have a rule that specifically states that network IDs or host portion cannot be all zeros or all ones. So we get a range of 1 to 126, and the 127th in the first octet would is not included because that's used for loopback purposes. Alright, so for Class A, the default subnet mask is 255.0.0.0, or in other words, the first 8 bits in the first octet belong to the network ID. And from that, we can derive the number of networks in a Class A IP range, or in a Class A IP range, yeah, which is 126, and the number of hosts per network comes out to roughly 16.8 million, and the total network and host combination comes up to 2.1 billion. Then we have Class B, and in Class B, the rule says in the first octet, the 8th bit has to have a value of 1, and the 7th bit has to have a value of 0. From that, we can derive the first octet range from 128 to 191. The default subnet mask is 255.255.0.0, where the first 16 bits belong to the network ID in a classful network. So the number of networks for Class B is 16,382. The number of hosts per network is 65,534, and it comes to roughly a billion point one total network and host combination. And going on to Class C, the binary rule says the 8th bit in the first octet has to be 1, the 7th bit has to have a value of 1, and the 6th has a value of 0 in binary form. And when we convert that, we will see that the first octet in the range for Class C addresses, IP addresses, it begins with 192, and it will go to 223. So the default subnet mask for Class C address is 255.255.255.0, or the first 24 bits of the IP address belongs to the network ID. And the number of networks in a Class C range is roughly 2 million, and the number of hosts per network is about 250. It's 254, and the total network and host combination is 532 million. So here we see the IP address ranges which are not used to assign to hosts, and so we have Class D, which has the binary rule such that in the first octet, the 8th, the 7th, and the 6th bit have to have values of 1 each, and the 5th has a value of 0. And from that we get the range 224 to 239, and again, it's used for multicast IP addressing, which I have plans to do a video on later on. And then we have Class C, which is used for experimental purposes, and we can see here the 8th, the 7th, the 6th, the 5th bits in the first octet are all 1s, and the 4th bit has a value of 0, and from that we can derive the octet range to be from 242 to 255. Alright, so we'll go on to the next slide now. Alright, so in this slide we have an explanation of how the IPv4 addressing rule works, and we will see how we get the decimal range for the specific classes of IP addresses from the binary form. So for Class A, the last bit in the first octet of an address must be 0, so that's the 8th bit. And here we can see just converting the first octet in binary form, which has a value of 1, so 1 times 1 is 1, and that's where we get the first octet. And we can see that at the end of the range, in binary form with that specific rule being applied. That so let's just add it. So the eighth bit has a value of 0. The seventh has a value of 64. The sixth has a value of 32. The fifth has a value of 16. The fourth has a value of 8. The third has a value of 4. The second has a value of 2. And the first has a value of 1. So 1 plus 2 is 3. 3 plus 4 is 7. 7 plus 1, or 7 plus 8 is 15. 15 plus 16 is 31. 31 plus 32 is 63. 63 plus 64 is 127. So the reason why we don't have 127.0.0 a mask of 8 is because it's reserved for loopbacks, but we get the range of 1.0.0.0 to 126.255.255.255 with the exclusion of 127. Alright, for class B, the last two bits, or the 8th and the 7th bit, in the first octet IP address must be respectively 1 and 0. And just using the very same method of converting each of the bits within the first octet to their values and adding them together, we get the decimal conversion. And here we can see it begins with 1 0, and that's followed, so 1 0, and with that we get a value of 128. 1 times 120 is 128, the rest is 0. Okay, and then here we can see that we have 128 plus, so this is the end of the range for class B. We have 1 0 1 1 1 1 1 1 for the first octet, and from that we get 191, and that is again the end of the range for the first octet for class B addresses. So for class B addresses, we have range going from 128.0.0 to 191.255.255.255. And then we have so class C, where the last three bits, 8th, 7th, 6th, in the first octet IP address must be 110. And it is very straightforward on how to convert from binary to decimal. If you want, you can pause it and you can try doing this on your own. So just multiplying the value for each of the bits in the first octet by 1 or 0, and then adding that together, you will be able to get the IP address range for the first octet. And you could do that for the other octets, and you will see how we get the different ranges for the various classes of IP addresses. Then we have classes, so that's done for class A, B, and C, and that is what is relevant for in terms of IP addresses which are assigned to hosts. Then we get into class D, which is used for multicast IP addresses, and for that the binary rule is very specific. It says the last 4 bits in the first octet IP address must be 110, and we can and using the binary form we get a range of in terms of decimal form of the IP address going from 224.0.0.0 to 239.255.255.255. Then finally we come to the last class of IPv4 addresses, and the binary rule is very specific here. It says the 8th, 7th, 6th, 5th, and 4th bits in the first octet IP address must be respectively 1, 1, 1, 1, 0, and just converting the decimal the binary range to decimal form, we get the decimal range going from 240.0.0.0 to 255.255.255.254. All right. And you could always look up Google on how to do binary to decimal conversions. It may um, it is a sort of calculation that you normally don't do, so you may want to get some practice if you want to understand how the IPv4 addressing rule works. All right, so I'll go to the next slide. All right, in this slide we talk about the differences between IPv4 public and IPv4 private addresses. IPv4 private addresses are non-routable through the internet, and they come in three different ranges. For Class A private IP addresses, it goes from 10.0.0.0 to 10.255.255.255 with a mask of 8 bits. Class B private IP address range from 172.16.0.0 to 172.31.255.255 with a mask of 16, and Class C private IP addresses go from 192.168.0.0 to 192.168.255.255 with a mask of 24. And all other IPs, all the excluded IPs in the private IP range are considered public IPs with the exception of 127.0.0.0 with a mask of 8 for loopbacks. So the pretty much leftovers of Class A and Class B and Class C IP addresses. So how does a private IP address is able to route to the internet? Well, it uses something called NAT, which is Network Address Translation, and also Port Address Translation. And what it does is it enables private IP intranets that use non-registered IP addresses to connect to the internet. And IPv4 public addresses are those that are routable through the internet. All right, let's go to the next slide. So in this final slide, I'm just going to go over a brief introduction to IPv4 subnetting. There are two types of subnets. You can have flat networks which are classful and have no subnets. You can have subnetted networks which are classless and have multiple subnets. With a flat network, the broadcast domain is at the classful boundary. For example, in a Class A network, there would be 16.7 million hosts per that network. And we'll see that there are serious disadvantages for having that many hosts on a single network. So subnetting is a solution to that. And subnetting is a method for segmenting a network into a number of smaller networks with their own addresses. It borrows bits from the host ID for the network ID, creating more networks for a proportionally smaller range of hosts. And what this does, it addresses the problem of reduced bandwidth per user, and in other words, it increases the bandwidth per user. It controls broadcasts, it implements security, and it is easier for administration. So these four issues are the issues that are problematic in flat networks. And and we can illustrate this by just taking a look at how a classful Class A network of 10.0.0.0 with a mask of 8 can be subnetted to networks with that are 10.0.0.0 with a mask of 30. So going from one network of 16.7 million hosts, we can go to 4,194,304 subnets of 4 hosts each. Alright, so this is the end of my presentation, and so there's definitely more to come. Alright, take care. Bye-bye.